single LED light bulb may cost only a few dollars, but with more than 15 billion units produced every year, LEDs have built an industry worth over $100 billion, illuminating nearly every corner of the planet. The journey begins with a semiconductor chip smaller than a speck of dust, moving through ultra-precise assembly stages measured in micrometers. Gold wire bonding thinner than a human hair, color conversion, protective encapsulation, and large-scale light testing follow. Today, this factory takes you deep inside that process, where chips that are almost invisible are transformed into billions of powerful light sources, brightening the planet every single day. Join Mana Tech Explorer and discover our next videos. For more than a century, humanity accepted a costly trade-off, burning vast amounts of energy to produce only a small amount of light. From Edison's incandescent bulbs, glowing with intense heat, to fluorescent lamps filled with toxic mercury, lighting remained inefficient and unsustainable. The world longed for a source of illumination that was cleaner, cooler, and far more durable. From this demand for change, LED technology was born. Yet, in its early days, LEDs were simply not powerful enough. For decades, they remained confined to supporting roles, appearing only as faint red indicator lights on control panels, while incandescent and fluorescent lighting continued to dominate. That limitation posed a defining challenge. If a blue LED could be created, everything would change. In 1994, Japanese engineer Shuji Nakamura discovered a semiconductor material that allowed blue LEDs to emit light reliably for the first time, making white light possible and ushering in a new era of human illumination. Every LED lamp begins with a semiconductor chip, and creating that chip starts with a crystalline foundation, most commonly sapphire. Before any crystal can be processed, human beings must enter an environment that is almost perfectly clean. The entire chip manufacturing area operates as a massive cleanroom, where a single microscopic particle of dust can ruin thousands of chips at once. Engineers and technicians must change into full protective gear, including one-piece cleanroom suits, hoods, masks, gloves, and anti-static footwear, before passing through high-pressure air showers designed to remove any remaining contaminants. Once strict conditions are met, sapphire substrates are loaded into epitaxial reaction chambers operating at extreme temperatures. Gases containing gallium and nitrogen are introduced, flowing across the sapphire surface and bonding atom by atom. These reactions form ultra-thin crystalline layers far beyond human vision. Through precise stacking, specialized semiconductor layers create a p-n junction. When electric current flows through this junction, charged particles collide and release energy as light. This is the exact moment an LED is born at the atomic scale. After epitaxial growth, the wafer appears smooth and mirror-like to the naked eye. In reality, its surface already contains millions of microscopic semiconductor structures that are not yet capable of producing light. To transform these structures into functional LED chips, the wafer undergoes photolithography inside a tightly controlled yellow light environment. The surface is coated with a light-sensitive material called photoresist, and ultraviolet light is projected through a precision mask, etching microscopic patterns with accuracy down to individual micrometers. Unwanted regions are washed away, leaving behind an intricate network of ultrafine circuit features. The wafer is then transferred into a vacuum chamber, where an extremely thin layer of metal is deposited to form electrical contacts. At this stage, the wafer has effectively become a massive light circuit board, containing tens of thousands of individual LED chips formed simultaneously and ready for separation in the next stage of production. When the microcircuit structure has been fully formed across the wafer, the journey of light enters a decisive stage, chip separation. Beneath its mirror-smooth surface, the wafer is a microscopic map containing tens of thousands of identical LED chips arranged in perfect geometric order. The factory employs a high-energy laser system with an extremely precise beam, guided along pre-calculated scribe lines between each chip. The laser cleanly slices the wafer into thousands of tiny square dies, minimizing cracking and residual stress that could damage internal structures. Once separated, each LED chip measures only a few tenths of a millimeter across, smaller than the tip of a needle. Yet within this tiny form lies a complete light-emitting region, layered semiconductors, and a fully formed PN junction, where even the smallest fracture can render the chip non-functional. The separated chips pass through an automated inspection system, where each one is briefly powered on to verify correct color emission and proper operating voltage. Defective chips are immediately removed, ensuring that only those meeting strict specifications continue to the next stage. Although the wafer has been sliced into thousands of tiny LED chips, they remain firmly attached to a thin carrier film. At this scale, robotic systems cannot pick up individual chips with micrometer-level accuracy while they are tightly packed. To solve this, the film is fed into a crystal expander machine, where uniform tension is applied from all four directions. As the film stretches outward, the chips gradually separate, increasing the spacing between them according to precise calculations. The result is a perfectly ordered grid, with every die evenly spaced and precisely aligned. Once expansion is complete, the film carrying the separated chips is transferred to an automated pick-and-place system, ready for the die bonding stage. Each microscopic LED chip is mounted onto a metal lead frame consisting of two terminals, the positive anode and the negative cathode. An automated die bonding machine dispenses a precisely controlled dot of thermally conductive adhesive onto a designated position on the lead frame. This adhesive serves a dual purpose, securely anchoring the chip while providing an efficient path for heat dissipation. As a result, both the volume and placement of the adhesive must be accurate down to individual micrometers. The expanded film carrying the separated chips is fed into the machine, where industrial vision cameras scan the entire surface, identifying the exact coordinates of each chip and the metal pads on the lead frame. Using this data, the system calculates positional offsets within just a few micrometers, ensuring extreme placement accuracy. The robotic arm then operates at near instantaneous speed, picking up, rotating, aligning, and placing each chip with remarkable precision. Each placement cycle takes only fractions of a millisecond. A gentle downward force spreads the adhesive evenly, preventing air bubbles and ensuring the chip remains perfectly level. Precision at this stage is critical. An alignment error of just 20 to 30 micrometers can cause color shifts, reduce LED lifespan, or lead to immediate failure in later processing steps. For this reason, once an entire strip of chips has been placed, the lead frames are transferred into a thermal curing oven. There, a stable temperature is maintained for several minutes, allowing the adhesive to fully cure and permanently lock each chip into position as a unified structure. Once the LED chip is fully secured onto the metal lead frame, the tray is transferred into an automatic wire bonding machine. A spool of 99% pure gold wire, just 18 to 25 micrometers in diameter, 3 to 5 times thinner than a human hair, is fed into the system. High-resolution industrial cameras scan each chip and its corresponding lead terminals, calculating their positions with micrometer-level accuracy. Using a combination of heat and ultrasonic energy, the machine forms a tiny gold ball at the wire's tip and presses it onto the chip's electrode to create the first bond. The wire is then drawn into a precise arc and lowered onto the metal lead to form the second bond. The wire is cut, and the machine immediately moves to the next chip. The process operates at incredible speed, yet every step demands uncompromising precision. Each gold wire loop is meticulously controlled for height, adhesion, and tensile strength to ensure reliable electrical connections and long-term stability. Once bonding is complete, technicians inspect every connection under high-magnification microscopes, removing any LED with weak or imperfect bonds to ensure only fully qualified components advance to the next stage. After gold wire bonding and initial inspection, the LED frames are transferred to the phosphor coating area. Raw phosphor powders are first weighed using an analytical balance with an accuracy of 1/10,000 of a gram, roughly 0.0015 grains. Depending on the target color temperature, engineers blend multiple phosphors, yellow, orange, pink, and other spectral modifiers, in precisely calculated ratios. The mixture is then sent to a high-speed mixer, ensuring the phosphor is evenly dispersed throughout the epoxy solution. Next, the phosphor epoxy mixture is loaded into the dispensing cylinder of a dotting machine. Thousands of LEDs, mounted on frames, are fed into the chamber, where ultrafine needles deposit an extremely precise volume onto each chip, accurate down to millionths of a liter. This thin coating converts the chip's native blue light into white dot or amber light, visible to the human eye. Once weighed and blended, the phosphor mixture is transferred into a high-speed rotary mixer, where it is evenly dispersed within a liquid epoxy resin to form a uniform coating compound. After coating, the entire tray of LEDs is placed into a curing oven operating at approximately 302 degrees Fahrenheit. At this controlled temperature, the epoxy fully hardens, permanently locking the phosphor layer in place and creating a uniform optical surface across all LEDs in the batch. Remarkably, no semiconductor chip naturally emits white light. LED chips always produce blue light. It is the yellow phosphor layer that transforms this blue emission into the white light we perceive, a hidden secret behind modern LED color technology, once the chips and gold wires are securely fixed in place. The entire lead frame strip is transferred to the epoxy molding area, where the LED's signature transparent lens is formed. Liquid epoxy resin is injected into steel molds containing hundreds of precisely shaped cavities, designed to create standard LED forms such as 5mm round heads, flat tops, or oval lenses. The filled molds are then placed into a circulating thermal oven, operating at approximately 248 to 302 degree F. Under this carefully controlled heat, the epoxy undergoes molecular cross-linking, gradually transforming from a viscous liquid into a solid, crystal-clear structure. Once curing is complete, the LEDs are released from the mold in their final form, a rigid, transparent plastic lens encapsulating the semiconductor chip and gold bonding wires, with the metal leads extending cleanly from the base. Once the epoxy has fully cured, the steel mold opens, revealing a long LED strip containing hundreds of individual lamps, appearing nearly finished yet still connected on a single metal lead frame. At this stage, the product remains a semi-finished component. Operators first perform a quick visual inspection of each strip to ensure there are no molding defects. The LED strip is then fed into a deframing machine, where precision-aligned cutting blades and metal punching mechanisms operate with extreme accuracy. In just seconds, the thin tie bars linking the LEDs are cleanly cut, releasing each LED package as an individual unit, precisely formed to standard dimensions. After being separated from the metal frame, each individual LED is fed into an automated electro-optical testing system. In a fraction of a second, the LED is powered on and illuminated, allowing industrial cameras and optical sensors to precisely measure brightness, color output, operating voltage, and color temperature, subtle deviations invisible to the human eye. Based on this data, the bending system sorts each LED into distinct groups according to brightness, color characteristics, and electrical voltage. Pneumatic mechanisms rapidly direct every LED into its corresponding compartment, ensuring that when assembled on the same light strip or panel, they emit perfectly uniform light without color shifts or brightness inconsistencies. From here, the qualified LEDs proceed to the lead forming and wire handling stage, where their metal leads are precisely shaped, aligned, and secured onto specialized conveyor systems in preparation for final packaging or downstream assembly. Only LEDs that pass all inspections move forward. They are carefully dried and sealed in moisture-resistant bags or trays, labeled with binning data, batch codes, and production dates. Finished shipments are then secured and transported worldwide to factories producing LED strips, displays, toys, and electronic devices, ready for final assembly and delivery to consumers. Today, LED lighting is an indispensable part of modern life. To explore more journeys showing how everyday materials are transformed through precise, meticulously engineered manufacturing processes, follow the channel for an inside look at industry down to the smallest details. Join Mana Tech Explorer as we explore the shipbreaking industry,